In this video, we're going to be looking at some important ideas like periodic behavior, periodic functions, and the sine, cosine, and tan functions. This is the first lesson of Unit 5, Trigonometric Functions, as part of my Grade 11 Functions course. If you want me to teach you this entire course, visit my website, tutor.ca, and enroll in the second teacher program, which includes video lessons, private tutoring, notes, and practice problems for every section in Grade 11 Functions. I hope you enjoy the video. Hello everyone, I hope you're doing well. Welcome to lesson 26 in the second teacher program's course on Grade 11 Functions. Here we're looking at similar content to section 5.1 from the textbook, which is modeling periodic behavior. As you can see, we're beginning our study of periodic functions. Okay, this is chapter 5, trig functions. We are going to be spending a lot of time understanding how we can use the actual graphs of the trig functions, the 6 trig functions, mostly the first 2, sine and cosine. But this chapter begins studying one of their essential, really important properties, and that's that they have periodic behavior. Okay, this is probably the most challenging chapter in the course because it requires you to know the previous content from this course very well, especially chapter 1 and chapter 2. And chapter 4, right? Chapter 3 was exponential functions. That's kind of a different topic. But chapter 1, chapter 2, gave us the route to talk about functions. Chapter 4 introduced all this new trigonometry ideas, right? All this new content. And then now chapter 5, we're going to be using that trig content, combination of chapter 1 and 2, to talk about trig functions. And so I don't want you to be shy to go back to chapter 1 and 2 and chapter 4 if you don't know a specific thing, right? If you don't remember exactly how to do horizontal stretches, then go back to the chapter on the lesson on horizontal stretches and just take a look there. There's nothing wrong with going back when you need to, right? It's much worse to try to continue when you're not ready to continue. So go back, try to get it, and then carry on with chapter 5. So the initial example that I'm going to start this chapter with is a Ferris wheel Ferris wheel example. So imagine you're on a Ferris wheel, okay, and you start. This is the Ferris wheel. If I can, maybe I should draw the circle first. Right, there's our Ferris wheel, and I am going to collect some data. Okay, I'm going to collect some data. I'm going to say as time increases, what happens to my height above the ground? Okay, so let's say the ground's right here, right? Say the ground's right there. And so when we start at the bottom of the Ferris wheel, we can say at time 0, we have a height of 0, right? Let's say it takes, 2, 3, 4, 5, 6. Let's say it takes 6 seconds to go all the way around. Let's just pretend that that's how fast the Ferris wheel is. So it takes 6 seconds to go all the way around, right? Then after 1 second passes, right, we would be here, right? After 2 seconds, and let's just take a guess, of how tall off the ground it is. Let's say the whole thing is maybe 10 meters. So 5 would be here, so maybe that's 2 meters, right? 2 meters there. After 2 seconds, I'm going to say the whole thing is 10 meters. Let's just take a guess there. Right? After 2 seconds, right, we would maybe be at 8 meters, right? After 3 seconds, we'd be at the top, right? And we'd be at 10 meters. After 4 seconds, we'd start coming down, right? And we'd be at maybe 8 meters again. And then at 5 seconds, we would be 2 meters off the ground again. I drew that kind of wrong, so let me draw it a little bit better, more symmetrically. So there we go, 2 meters again. And now at 6 seconds, we would return back to 0. What do you think 7 seconds would be? We'd be at 2 meters again, right? We would keep cycling through this for as long as the Ferris wheel keeps going at the same speed, right? This data would just cycle. So 8 seconds, I'd be at 8 meters again, right? 9 seconds, I'd be at 10 meters again. 10 seconds, I'd be at 8 meters again, right? 11, I'd be at 2, and 12, I'd be at 0. So you see how every 6 seconds, the pattern continues, right? So every 6 seconds, the pattern repeats itself. So try to just take that in for a second, right? That we have a type of data that I'm measuring here that repeats itself every certain number of seconds. And in this case, it's 6 seconds. Okay, and it's very important. That's the main idea of what we're trying to get at. So we describe this data. We say that this data is periodic. Okay, periodic means it has a pattern which repeats. So it has a pattern which repeats regularly. Right? So regularly means every certain number of time that goes by, seconds or whatever. Okay, oops, that's for later. So that's essentially the idea of periodic behavior. This is what periodic behavior is. Okay, so the section is called modeling periodic behavior. Periodic behavior is when you're collecting some kind of data, right? Or you have a function or you have something that's behaving in a periodic way. And what a periodic way is it's a pattern which repeats regularly. Okay? Okay. So we can say that the period of this data is 6 seconds. Because it takes 6 seconds to get back to where I started. Right? It takes 6 seconds to get back to where I started. Let's graph all this, actually. You know what? How about let's graph all of these, all this data that I had here, right? So it started with, and you'll just see it slowly showing up here as I type everything in, right? So 0, 0 was one of our points. And then at 1 second, we were at 2. At 2 seconds, we were at 8. At 3 seconds, we were at 10. At 4 seconds, we were at 8. At 5 seconds, we were at 2. At 6 seconds, we were back at 0, right? So we kind of have this kind of like curve going up like that, right? We climb really quickly in the middle, and then we come back down. And then we just repeat it all again, right? So I can't copy everything. So at 7 seconds, we were at 2 again. At 8 seconds, we were at 8, right? At 9 seconds, we were at 10. And then at 10 seconds, we were at 8. And then at 11 seconds, we were at 2. And then at 12 seconds, we were back at 0, right? So you see our height as a function of time, if you made a function to connect all these dots, right, would be periodic. And that means that you're repeating every certain number of steps. And we say that the period, right, the period of a function, the period of a set of data is how much time has to pass by, or how much whatever the independent variable is measuring has to pass by before it repeats itself. Okay? So let's take a look at the definition of a periodic function. Okay. So a periodic function is a function which matches periodic data. Okay? That means it repeats the pattern in cycles. The length of a cycle is called a period. So the length of a cycle here was 6. 1, 2, 3, 4, 5, 6, right? So there's 6 steps here. 1, 2, 3, 4, 5, 6 to get to the end, right? And then we repeat. 1, 2, 3, 4, 5, 6. We repeat again, right? So the length of the pattern here is 6 seconds. The period can be measured in time or any other measurement. It's the independent variable. Whatever the independent variable is measuring, that's how long that is. Okay. Okay, so far we've talked about what periodic data is, what a periodic function is, okay, what a period is. So a period is the length of the cycle. Okay. Now let's take a look at some graphs of periodic functions. Okay. So I have a couple here. These are actually from the textbook. So I have these. Well, actually, they may or may not be periodic functions. And we're going to determine if they're periodic and what their period is. Okay. Okay, so there we go. There's my 4 examples. So let's take a look. This function is periodic. Because, look, we start here. How long does it take for me to get to the exact same point in the cycle? Well, the next same point in the cycle is right here, because look, it goes kind of like up by 3 over 2, down by 3, over 3, up by 3, over 2, down by 3, right? So this is, you know, we go 2 spaces and then we go up. So this is the next point where that happens, 2 spaces and then you go up. So it is periodic because it's repeating that, right? You can kind of imagine that this chunk, what I've kind of boxed here, right? Maybe I'll box it in this, right? This, what I've boxed right there, right? Repeats. You can pick that up and move it along the graph, and that pattern repeats. How long is that period? It's 1, 2, 3, 4, 5 units long. So this is periodic, and it's 5 units long. Okay. Before I do this example, let's do another example. Let's do maybe this one here, right? So you don't have to measure from the the period is 5 units long. For this one, you don't have to measure the period from the y-axis. I could say, let's just start here. Let's see if it's periodic here, right? So if I start here, when's the next time we have that part of the cycle? It'll be right there, right? Right? How long is that? 1, 2, 3, 4, 5, 6. And does it look like that's repeating over and over again? Yes. It looks like that's repeating over again. That exact thing you see in this box, right? That exact thing. I could move that to the right or to the left, and it would lay on top, right? It would overlap the old graph, right? So if I picked this up, just that what's in that box, grabbed it and moved it over here, it would match exactly, right? It'd be the same thing in the box. Okay. So this is periodic. And it has a period of 1, 2, 3, 4, 5, 6. Period of 6. And that's the same thing as if I measured the period from here, right? From here to here. Same. 1, 2, 3, 4, 5, 6. Same. So period of 6. Doesn't matter where you measure it from. Just 2 points in the cycle. Two of the same points in the cycle. Right? Okay. Let's look at this example now. So it may look like it's periodic because it's doing the same thing every time. But what you want to imagine is, can I just like take a chunk, like for example, you know, from here to here, right? Take this chunk, okay, and move it anywhere else. Is there 2 points, right? 2 points here where you can see like the cycle is complete, right? It's going back to the same point again. Because you see here, right? Like we go to the same y value again right here, right? So it goes from here to here, and now the cycle repeats. But here, there's no point like that. It's not like we go here, and then like over here, it starts again going up like this, right? That just doesn't happen. Or like, maybe I choose this point. It's not like over here, right? We're going again, 2 over, 2 up, to the side, 2 up, right? So there's nowhere repeating. This is not periodic. There's a pattern, right? But it's not periodic. It doesn't have a period. There's no like, this would be an infinite period, right? It starts somewhere over there and ends somewhere over there, right? Infinitely far in either direction. So there's not periodic. There's no period. It's just a repeating pattern, okay? Which is not the same thing as periodic. So see, this has a repeating pattern. You're going up 2, over 2, up 2, over 2. But it is not periodic. It's not like you repeat itself entirely somewhere else. One final example. Let's take a look at here. Well, okay, so let's see. This starts, you know, we can choose anywhere in the cycle. So maybe I'll start like here, right? To here, right? Compare these 2 points. These are at the same position in the cycle, right? The bottom. How long is that? 1, 2, 3 and a half, I guess. 3.5, right? So it is periodic. And the period is 3.5. 3.5, whatever the x units are. Okay. So we've defined periodic, we've defined periodic functions, we've looked at periodic behavior, we have talked about what a period is of the thing, we've looked at the 4 graphs and seen what their period is and if they're periodic. Let's take a look for a second at the formal definition. Formal definition of periodic. It's helpful. You don't have to really understand this, but it's good to know the formal definitions of things. So a function f is periodic if there exists some p-value such that the following equation is true. F of x plus p equals, or I'll do it like this. F of x equals f of x plus p. As in, I can input some number x and input some number x plus another number, and that will be the same thing. For example, in our question up here with the Ferris wheel, right? If this was a function, right, then let's say f of 1 equals 2, right? So if f of x is the height and x is the time, right, f of 1 equals 2. What about f of 7? That's also 2, right? But 7 can be written as 1 plus 6, right? 1 plus 6, right? So f of 1 plus 6 is also 2. What about this pair? What about f of 3 was 10? What about f of 3 plus 6? That would be f of 9, which was also 10. What about f of 5? That was 2. What about f of 5 plus 6? That would be f of 11, which was also 2. So the point is a periodic function is a function that you can shift the input over by one period and you'll get the same answer. Let's take a look at a little visualization of this, right? That's one period there, right? Doesn't matter where I start the period or end the period. It's one period because it starts at that point and it ends at that point in the shape. Here's our periodic function. So f of 2 is 2, and f of 2 plus a period is also 2. So p here is the length of your period. Is the length of the period, right? So a function f is periodic if it has some period, right? If it has a period. Okay. So this is essentially saying you can f of some number, right, is the same thing as f of that number plus one period. In fact, it's not even just one period. You could go over 3 periods, right? So if you look at this graph here, right, I could go over one period and then over another period, and I'm still at the same point. The point of the period is that you exactly end up at the same y value that you had before, right? The same output value from the function that you had before. So I can move over a period, I can move over another period. In fact, I can go backwards a period too, right? I can go here, go back a period, I'd end up there, and that's the same point. It's not exactly numerically the same point, but it represents the same point in the cycle, right? Represents the same point in the cycle. So periodic behavior is trying to understand data that repeats itself. And now trig functions are very useful for this. We're going to talk about this in the next section, but trig functions repeat themselves. And so that's why they're important to study, because they can be used to study anything that repeats itself, like Ferris wheels. Okay, let's take a look now at one final topic. Now, you know the formal definition of periodic. Let's take a look at one final topic, okay, and that's called amplitude. Okay, amplitude is essentially just a number that relates to the graphs of periodic functions, okay? I'm going to put all these graphs back here just so we can calculate. Well, sorry, that's not periodic, so we don't care about that one, right? But this one's periodic. And essentially, it's measuring how high up, how far away. So let me measure it. It's measuring how far away the graph goes from the x-axis. So for example, if I go here, right, this function has a certain distance it goes from the x-axis, right? But what about this one? Don't worry about what I'm typing there for a second. What about this one? That periodic function. It goes a lot further from the x-axis than this one. So this red function has a bigger amplitude than the function I showed here. Now, of course, that's supposed to repeat forever, but because I just didn't do it forever, right? So I had to do it manually, so there's that, right? So, but this red function has a much bigger amplitude. I'll make it a little smaller so you can see it on the screen, right? But there. It has a bigger amplitude because it goes further from the x-axis. So essentially, we're measuring how far away the graph goes from the x-axis. How we do that, we say the amplitude A The amplitude A is just the maximum value minus the minimum value divided by 2. Essentially, you can think of it like the distance. Let me just type it. It's the distance from the max to the min, right? So essentially, how far vertically do you have to travel to go from the max to the min, and then split that in half. And that's kind of like the average distance from the x-axis, right? Half of that would be the distance from the x-axis. So divided by 2. So let's calculate that for all of these graphs here. What is the amplitude of this graph? The amplitude of this graph is the amplitude is the max value minus the minimum value divided by 2. The max value was 2. The minimum value was -1, right? So 2 minus -1. Important you keep the negative sign, right? Minus -1. That's 2 plus 1 over 2. It's going to be 3 over 2. And that's fine. 3 over 2. 1.5. Right? That's for this graph. Now let's take a look at this one. I'm just going to move it down so we have a little bit more space, right? What about the amplitude of this one? It's the max, which is 1, minus the minimum. Minimum is -1 again, divided by 2. So it's 1 plus 1 over 2, which is 2 over 2, which is 1. So the amplitude of this function is 1. And finally, let's take a look at this periodic function. So we say the amplitude is the maximum. Maximum looks like it's about 1.5, right? 1.5 minus the minimum. Minimum is 0, right? It touches the x-axis. Divided by 2. So that's 1.5 over 2. It's good to turn decimals into fractions. So 3 over 2 over 2, right? How do you divide fractions? That's 2 over 1. So it's going to be 3 over 2 times 1 over 2, which is 3 over 4, which is 0.75. So there is the amplitude, right? Max minus the min divided by 2. In this case, you have to do a little fraction work here, right? But 0.75, 1, and 1.5. These were all our amplitudes. And so they kind of like, the bigger the amplitude, the further you go from the x-axis, the bigger the jumps you make, right? If we look at our Desmos example, what was the amplitude of this guy, right? Well, it was 10 minus 0 divided by 2, so 5. The amplitude's 5 in this particular case. What about this guy? What about, not the red one, but the one that I wrote originally, right? It's going to be 3 minus 0 divided by 2, right? Is going to be, well, 1.5. Finally, I just want to show you, this is the end of the lesson already. This is everything. I know this is only 22 minutes for me, and I haven't even made any cuts, so it's gonna be a short lesson this time, right? Because there's not very much in this section. But I just want to show you the sine and cosine function, right? So if we do f of x equals sine of x, okay? I don't know if you're ready for this, right? F of x equals sine of x, right? That means that I put in a number x, the height above the graph is the sine of x. It looks like this. Now you may be wondering, why does it do a squiggly line? Why does it repeat forever in every direction, right? What's happening here, right? Very good question, and we're going to talk about that. In fact, actually, that should be in degrees, so you know what? Leave it like that. We're going to talk about that in the next section. Cosine of x, so I guess I'll say g of x equals cosine of x. So it looks like that, the blue one. It's very similar to the sine one. And now, so cosine, that's sine. Now tan of x is a funny one. Remember, tan of x sometimes doesn't exist. Remember, when we divide by 0, when cosine 0, tan doesn't exist. So it's going to be a kind of a more complicated function. We have something like this. We actually have a bunch of asymptotes here, right? So it approaches this line, right? But it never touches it. Okay, and that's the topic for next lesson, but that is everything, all the content I wanted to talk about in this section here. Okay, I just want to do one last example before I finish up the lesson here. So just say an example. If I tell you a periodic function, f of x, with a period of 8 has the following values. F of 1 is 3. F of 2 is 4. F of 11 is, not 11. F of 3 is, 7. Then what is f of 9, f of 10, f of 11, and what would maybe f of 17 be, and f of negative 5 be. Okay, there we go. This one I made up on the spot, so sorry, that took a second for me to think of. What are all these values, right? So all we know is f of x is periodic with a period of 8. That means every 8 increases of x, you repeat. We know f of 1 is 3, f of 2 is 4, f of 3 is 7. So that also tells us that f of 1 plus 8 would also be 3. F of 1 plus 8 would also be 3. Because you're just going one cycle further. So what's f of 1 plus 8? F of 1 plus 8 is 3. F of 9 is 3. I just discovered that f of 9 is 3. So one cycle further is still the same value. What about f of 2? What if I go one cycle further? F of 2 plus 8, that'll also be 4, because I'm just going one cycle further. It'll be the same point in the cycle, though. So f of 10 is 4. I just learned f of 10 is 4. What about for f of 3? F of 3, right? F of 3 plus 8, go one cycle further. That's 7. 3 plus 8 is 11. I just learned f of 11 is 7. What about these last two? F of 17, right? So f of 17, how can you make 17? 17 is 16 plus 1. So if I take f of 1, add 8, I know that's going to still be 3, right? I know it's still going to be 3 because I know these facts. I'm going to box them just to be completely clear here about what I know, right? So I know f of 1 is 3. So f of 1 plus a period plus another period is still going to be 3, not 7, 3. So f of 17 is 3. Nice. I can also go backwards a period, right? So if I say f of, well, we're going to negative 5. So how do I get negative 5? Well, 3 minus 8 is negative 5. So f of 3 minus 8 is, well, f of 3 was 7. So f of 3, and then you go back a period, it's still going to be 7. I'm just going back a period. So f of negative 5 is equal to 7. And I just learned that there. So there you go. That is all. That's just an example I went to there to just use the definition of a periodic function there quickly to talk about that. And there we go. That's our first lesson in chapter 5. Pretty simple lesson. Just new concepts to think about, right? And yeah, so we'll talk a lot more about it in the next sections where we talk about the sine and cosine functions, which are going to be used for this entire unit. So for now, if you have any questions, you can book a session with me or another instructor. And you can also email me at secondteacherprogram@gmail.com if you have any questions. Thank you so much for watching. I hope you enjoyed, and have a great day. Thank you for watching the video. Remember, if you want me to teach you the entire course, visit my website, tutor.ca, and enroll in the Second Teacher program, which includes video lessons, private tutoring, notes, and practice problems for every section in grade 11 functions. Have a nice day.